I'm happy to introduce our next talk, Reimundo Heluani from IMPA, that will tell us about finiteness of the first chiral homology group.
Thank you, Julia, and thank you all the organizers for the invitation. It's a pleasure to be here, although it'd be much nicer to be there. But anyways, it's nice to see you, at least virtually. I'll be speaking about the very same thing that I have been speaking for the last 6-7 years. This is some complex that Bayesian and Drinfeld defined in the algebraic setting related to a Riemann surface, a vertex operator algebra, and it gives some subtle homological invariance of the representation theory of this infinite dimensional Lie algebras. So I only have 7 slides. I only have 6 slides. The work that if I get to say something, is going to be on the very last slide. That's going to have something about the first kind of homology group, and that's joint work with Jethro van Egeren. There's 2 papers out. There's 3, perhaps, if you count another one. But those 2 are going to be the main references to the last slide. So, oops. Let me just see if I can shift pages here. Yeah. Okay. So I'm going to be talking about vertex algebras with briefly defining them, but just before going there, let's recall some things that the category of representations of the affine Kac-Moody algebra or the Virasoro algebra, or if you know what it is, the W algebra at admissible levels have in common. So if you look at representations of the affine algebra at integral positive level, for the Virasoro algebra, not an arbitrary central charge, but when the central element acts by a particular rational number, here P and P prime are co-prime numbers, then these categories have something in common. You have finitely many irreducible representations, as long as you just consider special representations, either your integral representations for the affine algebra, highest weight representation for Virasoro, regular admissible representations for W algebra. Put as many adjectives as you want, but you get something very nice that is a modular tensor category. There are no non-trivial extensions between the irreducible representations of these algebras for those particular levels, for those particular central charges. And so these infinite dimensional Lie algebras are a good source for people that study modular tensor categories. So there are 2 things that I want to focus today on. One is this finiteness condition that is about having finitely many irreducibles. And the other one is the word modular in point number 3. So this is going to be a very naive way of introducing a modular parameter, but the point is that for all these 3 kinds of algebras, if you look at representations, they are infinite dimensional, but they're naturally graded, and they have finite dimensional graded pieces. So this having finite dimensional graded pieces and them being graded is part of the conditions that you would add to your representations, like being highest weight and so forth. The point is that, well, they're not naturally graded by the integer numbers. The best grading happens to be for some rational numbers. You have a lowest energy space or lowest degree space that has some rational energy or rational degree. And then every other degree space every other graded space has a grading that is just an integer difference from the lowest one. So when you're in that condition, you can just look at the graded dimension of that representation. So this is just this formal sum. You just put q to the n times the dimension of the nth graded piece. And now what happens magically is that for all these 3 kinds of algebras, those characters of irreducible representations, this formal power series actually converges, and it converges to a holomorphic function on the upper half plane. This is somewhat mysterious. If there's a reason, I can't really think of a reason that is not a physical reason for this happening. But this was certainly mysterious when this appeared. For the affine algebra, this was settled in the 80s. For the Virasoro algebra, this was settled in the 70s. For the W algebras, this was settled in the 2000s, in the early 2000s. But well, now that we have a modular parameter, this tau, which is in the upper half plane, we may ask what happens if I just apply a Möbius transformations to that tau. And what it happens is that if you correct your characters by q, well, there's a power of q, this c there is the central charge. Then if you have finitely many characters for irreducible representations, those finitely many guys span a finite dimensional representation of the modular group or of SL2Z. here SL to Z acts by Möbius transformations on tau. So that's quite interesting. And here I'm using something that Susan mentioned. For the Virasoro algebra, that number C makes sense. This is how the center is acting. For the other algebras, I'm exploiting the fact that representations of the affine algebras, they hide a representation structure for the Virasoro algebra. So the Virasoro algebra acts on any representation of the affine Kac-Moody algebra as long as the level is not critical, and this C is the number by which the center acts. All right, so this is the situation that I want to understand. And the title on that slide mentions zeroth chiral homology, and I want to define that and say why chiral homology has to do with this situation. So in particular, I want to explain why finiteness of the zeroth chiral homology group implies that there are finitely many reducible representations and that you're going to have some modularity for those characters of those representations. So this is all theory. All I'm going to say until slide number 6 has been settled in Zhu's thesis in 1996. Okay, so this is going to be a quick slide defining what a vertex algebra is. If you know what it is, then this is just going to set notation. If you do not know what it is, just think of V as either the affine algebra or the Virasoro algebra, or its universal enveloping algebra if you wish. Properly, it is the vacuum representation of both either the affine algebra or the Virasoro algebra. But a vertex algebra is a vector space with a funny looking multiplication. So the multiplication doesn't really land on V itself. It lands on power series, on Laurent power series of V. So you give me two vectors, and this guy here is not an element of V, but it's a Laurent power series with coefficients in V. And that multiplication has only one axiom. So let me write this axiom. That axiom is very scary looking. You see this and you get scared, but it's a horrible looking axiom. However, if you only concentrate in what's highlighted there, just the red part of that axiom. You see, this really looks like a Leibniz condition or a Jacobi condition. This term here, let's concentrate on this term. This term looks like A times B times C. This other term looks like B times A times C. So if this right-hand side of this equation wasn't there, this axiom would want to look like commutativity. So if the right-hand side was were zero, this would look like A times B is equal to B times A. Conversely, if the second term on the left-hand side is not there, then the right-hand side looks like A times B, and then multiply that times Z. So this equation would want to be associativity, would want to be that A times B times C is equal to A times B times C. So this equation that involves three terms is an equation that relates A times BC, B times AC, and A times B times C. And those kinds of relations, triary relations, they want to look like either Jacobi or Leibniz. And now there's the point that we have a family of those relations parametrized by these rational functions. So these are rational functions on two variables that have singularities at Z is equal to 0, W is equal to 0, or Z is equal to W. So if you wish, these symbols residues here mean the coefficient of Z inverse. So here's the coefficient of W inverse. And this residue here means expand this in powers of Z minus W and take the residue, the coefficient of Z minus W to the minus 1. So this is a family of equations parameterized by these rational functions. But all of these equations, they want to be like Leibniz or Jacobi. Okay, so that's it. That's a vertex algebra. It's a vector space with these multiplications. If you know what a vertex algebra is, you'll be appalled by this definition because I haven't introduced a unit. But this is all you need to define the complexes that I will use. However, let's introduce the unit because that's something that people are used to. This is called the vacuum vector, and it's a unit for the left multiplication. So if you have a unit, 1 times A is A. Now our multiplication is not really commutative because of this appearance of this right-hand side here. So A times 1 doesn't need to be A, but it's A plus something in V of Z. Oh, here there's actually a mistake. I want to make sure that this is Z times V of Z. So there's something of order Z here. but it doesn't have a singularity. In principle, the multiplication of two vectors is a Laurent series. And here I'm saying, well, it's not a Laurent series, it's a Taylor series, and it starts by A. So modulo Z, this is a unit. All right, so that's a unit. This is what people call a vertex alpha. That definition there is equivalent to what most books would define as a vertex algebra. And historically, from representation theory, I said that we have typically an action of Virasoro. So let's impose that. People impose that you have a conformal vector, that is, that you have a very special vector whose multiplication by that vector makes your vector space V into a representation of the Virasoro Lie alpha. So if I multiply by this W, then I get a Laurent series. I put names to the coefficients of that series. This defines these operators Ln. And these operators Ln, the condition here is that they define a representation of Virasoro on V. So vertex algebras that have these conformal vectors are called either conformal or vertex operator algebras. All right. So having a vertex algebra, it's with that definition, it's very simple to describe what a module for a vertex algebra is, because you just change where the multiplication lands. So if now I have a vector space M and a multiplication from V acting on M, satisfying exactly the same axiom that I had before. It doesn't make any sense to now ask for something for M times 1, but 1 times M makes sense, and I would require that that's a unit. So this is the definition of a representation of a vertex algebra, just as you would do for rings. You just change your action by multiplication. And in particular, this says that a vertex algebra is a module over itself. M is equal to V is the same axiom that I had before. In addition, you ask if you have a conformal vector, you will ask that one of the modes, L0, acts with eigenvalues bounded below and with finite dimensional generalized eigenspaces. So this is the condition that the category of representation is nice. If you think about this, this gives me a way of writing a character as in the previous slide as the trace of Q to the L naught. The fact that I have generalized eigenspaces would make it that logarithm of Q would appear in that trace. I'm going to have a polynomial logarithm of Q's. And if L naught acts diagonally, so acts semi-simply, not generalized eigenspaces, but actual eigenspaces, that would be just a formal power series as in the previous slide. But this is the condition that makes the category of representations nice enough so that I can talk about characters. That's all. All right. Let's go to the chiral homology. I said that I was going to spend most of my time in chiral homology in degree 0, and this is what chiral homology in degree 0 is. So you give me an elliptic curve that's just a quotient of C, the complex numbers by Z2. That's our parameter tau in the upper half plane appearing there. So here I should probably say that tau is in the upper half plane. So this tau is in H, and hopefully Beamer is gonna make that red thing disappear. And our complex looks as follows. In degree 0, we put this V. So this V here is in degree 0. This is in degree 1. This whole space is in degree 1. And the differential here decreases degree by 1. So it's a homological complex. So what is that? In degree 1, we have a tensor product of V with itself, and we have meromorphic functions on the elliptic curve that may have poles at one point. This one point is the marked point of the elliptic curve. From this perspective is the image of 0, or from this perspective is the image of 1 in C star. And the differential is very simple. There's only one thing that we can do. If you give me two vectors in V and a function, then we have a product already, which is take the residue, expand that function that might be singular at Z is equal to 0, and apply the multiplication of A with B. So this looks like just the multiplication of A with B. Let me write a shorthand for that multiplication. It's going to be AFB. I'll use that later. Okay, so that's a complex. And here's a definition. The zeroth chiral homology of the elliptic curve with coefficients in the vertex algebra V is just the homology of that complex in degree 0. And that homology has deep connections with the questions with the points that I raised in the first slide, finiteness of the number of irreducible representations and modularity of the characters of those representations. So let me say why or how. So the space of functions that we are allowing here is very restricted. We have one function, well, or just a complex number value of functions that are regular on the whole elliptic curve. These are just the constant functions. So they're all a multiple of the constant function 1. Then we have only one function under multiples of that has a pole of degree 2 at the singular point. There's no function with a pole of order 1 because, well, the residue theorem would tell you that it's impossible. And Riemann Roch would tell you that there's only one function with a prescribed pole for 3 of order 3, 4, and so forth. And they're all derivatives of the function that you have with the pole of order 2. So this is the Weierstrass P function, and you have all the higher derivatives. And these are all the functions, they span the space of functions that are singular at one point in an elliptic curve. So this quotient here, the chiral homology, is a very concrete quotient. You have the vector space V, and you divide by the images of applying this F product, where F is 1. I'm writing 1 as Z to the 0. Just to not make it confuse. I mean, if I had A1B, that would be confusing for people that know what vertex algebras are. And then the Pth product, and then I should put here A P prime B, A P second prime B, but the axioms of vertex algebras allowed me to trade derivatives on this function F by derivatives of A. So this is enough. This is actually that quotient. I can stop right there. And this is the chiral homology. Dually, if you're looking at the dual of chiral homology, then you'll ask for a linear function on V that kills derivatives. So whenever I apply F on G of something, then it should be 0. So that's going to be a vector in the dual of chiral homology in degree 0. Okay. So far I have only defined a vector space associated to a vertex algebra. If you do this for the affine Kac-Moody algebra, that's an interesting exercise to try to compute this. This is a highly non-trivial segment to compute this, that this space is finite dimensional and that the dimension is the number of irreducible integrable representations of the Kac-Moody algebra. But there's one thing that I haven't talked about, which is where tau plays any role here. And the only appearance of tau in this quotient here, in this quotient, the only place where tau appears is in this function P. This function P is a function that depends on Z and tau. So that's the only appearance of tau. So for each parameter tau, we have this vector space. And the point is that as we move tau smoothly on the upper half plane, or as we move x on the moduli space of elliptic curves, these vector spaces H0 move and they find a vector bundle on the moduli space of elliptic curves with a flat connection. So let me describe you what that flat connection is. So we're going to use a formal integral of the Weierstrass P function. This is the Weierstrass zeta function. It has a pole of order 1 at that marked point, but it's not an elliptic function. This zeta is not well defined on the elliptic curve x, but it's well defined on the complex numbers. It's a meromorphic function on the complex numbers that is not biperiodic, but it has a pole of order 1 at each lattice point. And now I'm going to define this endomorphism of V, this delta, by using the two special vectors, the two special points that I have. I have the conformal vector W, and I have the special function Z. And I'll define this nabla to be D of that. So in principle, this vector here, which is in V, does not need to vanish in chiral homology. If this zeta function was an elliptic function, this would be 0 in chiral homology because it's the image of something in the of the differential. But this zeta is not really in the complex. In my complex, I only allowed elliptic functions. So this is a vector that is not necessarily zero in chiral homology. So dually, I could look at linear functionals in V that kill differentials. So these are vectors in the dual of chiral homology. But additionally, I would ask that instead of killing this guy, this doesn't need to be zero because zeta is not an elliptic function, but then that it satisfies explicitly this differential equation. So that is the condition of being a flat section on the bundle of chiral homology. Of this bundle that we have of chiral homology, well, let me write it like H chiral 0 dual, that this is a bundle on the moduli space of elliptic curves with one mark point. So a conformal block is a section, a flat section of this bundle with this connection, but very explicitly I defined it to be a linear functional on V star that satisfies this differential equation with respect to time. And the theorem of Joux that settled this theory about 20 years ago, 15 years ago, is that the characters of irreducible representations, when the vertex algebra is rational, this means when you are assured that you don't have non-trivial extensions between irreducible modules, and when this chiral homology is finite dimensional, then the characters satisfy that differential equation in particular, and they span all of the space of conformal blocks. So this is a very interesting theorem in that, well, I'm using that I don't have extensions. That's a hard theorem to prove for most algebras. But after you do this, even assuming that you have infinitely many representations, if you prove that the chiral homology is finite dimensional, well, you have only finitely many irreducibles, and the characters satisfy an explicit differential equation. And now you can use the general theory of ordinary differential equations to expand that solution to those equations near the singular point. This differential equation has a singularity as q goes to 0 or as tau goes to I times infinity. So that's the special point on the moduli space. This is corresponds to the nodal elliptic curve. And you expand your solutions there, and you use the general theory of differential equation to prove that these characters converge. So that's the hard part of the theorem, just a careful analysis of this differential equation close to the singular point. All right, so now that's a connection with chiral homology and characters. Characters are sections of the dual of chiral homology. And now I'm interested in finding what are the conditions so that this happens, that I have finite dimensional chiral homology. Namely, I have a vector bundle on the moduli space of elliptic curve instead of just a quasi-coherent sheaf on the moduli space of elliptic curves. Okay, so I have, oh shoot, I have only 1 minute and I haven't reached slide 7. So let's rush. This chiral homology is bounded by in two ways. I can either look at the limit as tau goes to infinity or q goes to 0, or I can look at a filtration on the vertex algebra and take an associated gradient. Both of the, so here's where the connection with Susan talks appear. So let me quickly say, therefore, that if I look at the limit as tau goes to I times infinity, then this quotient that is not the full chiral homology, remember I need to also quotient by a z to the 0b. So this is larger than chiral homology, but this goes to an associative algebra known as the Joux algebra of V. To give you an idea, for the affine vertex algebra, the universal affine vertex algebra, this Joux algebra is the universal enveloping algebra of the finite dimensional G. So knowing that this is finite dimensional, that's already telling us that the chiral homology is finite dimensional. So another way of looking at this is for every vertex algebra, you can look at a filtration. You can filter by the number of derivatives that you have, and the associated graded is a commutative. This guy here is a commutative differential algebra graded, and the derivative has degree 1, and the degree 0 piece surjects into this associative algebra. So the filtration of V gives a filtration to this guy, and the associated graded to this guy is smaller than A0. So if A0 is finite dimensional, you already have finite dimensionality for chiral homology. Okay, let me just finish in let me just take 2 minutes. here's a refinement of that statement. Since I needed to quotient also by a z to the 0b, then actually I need something less. I need that the degree 0 Poisson homology of A0 is finite dimensional to get that chiral homology is finite dimensional. All right, so let me just quickly say what the first chiral homology is and finish here. So the first chiral homology group, as you might have guessed, is just completing that complex and making it larger, including higher powers of V, so more factors of V and more factors of the elliptic curve X. So now I have, instead of one copy of the curve, I have two copies of the curve minus a point, and then I'm taking out the diagonal inside of them. So I'm allowing functions. This function f of z of w are exactly what we've seen before. They have singularities at z is equal to 0, w is equal to 0, or z is equal to w. Now, there are many more functions than just p and their derivatives of p, but you have control over what those elliptic functions are. And the differential is just exactly as we did written before, using the f products. So this looks like a Hochschild differential that people in Hopf algebras are very happy to look at. So this has the flavor as the Hochschild differential, but just for parameterized by this extra function f that is an elliptic function. And it turns out that the axiom that I wrote for vertex algebra is exactly the statement that this is a complex, that this squares to 0. For any function f with singularities exactly at the points where I wrote, the axiom that I wrote is the statement that d of d is equal to 0. That's just the definition of what AFB is. Okay, so the theorem is as follows. We're interested in knowing when the first chiral homology is finite for representation theoretical implications that I'm not going to have time to describe, but I'm going to say that the first chiral homology is finite dimensional. So you get a vector bundle with a flat connection on the moduli space of elliptic curves if the first cohomology of this complex for A0, the first Poisson homology, is finite dimensional. If you notice, this is the differential here on the last one. The 0th Poisson homology is the quotient of A0 by the Poisson brackets, which was the condition for the chiral 0 homology being finite dimensional. But here, there's an extra condition that is the condition that this graded commutative algebra with a different with a derivation has a finite dimensional first Koszul homology. Koszul homology is because we have a derivation on this algebra. So any algebra with a derivation, that's by definition a map from omega 1 to A, and you extend that to make it by making a derivation of this complex. So now I'm requiring that the homology is finite dimensional at this spot instead of this spot. And well, so the connection with Susan's talk is that even for Virasoro, it's very hard to know when that first homology is finite dimensional. So it's not clear that it's 0. This depends on, so that Koszul homology is 0 if and only if this commutative algebra is freely generated by the degree 0 piece. This means that it's the algebra of functions on an arc space. And this is known for Virasoro, for example, for P and P prime being 2 and anything. But it's not known, it's not 0 for any other combination of the central charge. And it's only known to be finite dimensional, different than 0, in one case that is very hard question to ask, which is the Ising case, which is central charge 1/2. Okay, so I am sorry that I took 5 minutes of your time. I was very slow at the beginning.